Okay, hello everybody again. We are in the final day of the first week, and today Craig Van Coevering is going to talk about extremal Kähler matrix and the moment map.
Okay, so thanks for the opportunity to give the talk. So I'll give this in like 2 days, and so the first talk today will be mostly a review of extremal Kähler metrics, and then next week I'll follow up with some original results using the symplectic moment map picture of the subject. So it's mostly the topic is mostly from the complex point of view. So I'll only assume that you have a background in differential geometry. So I'll start from the beginning. And almost Hermitian manifold is manifold with almost complex structure. So it's a endomorphism whose squares the identity and a Riemannian metric that's compatible with J. So and so then it has a skew symmetric two form called omega, which is defined in terms of the metric and the almost complex structure. So it'll be called the Kähler form. Only that's mainly just preserved for the special case we'll consider where this is a Kähler structure. But this is a very general structure. So then there's the special case that's very nice to work with is the case of a Kähler structure. So that's an almost Hermitian structure where where this is the Levi-Civita connection of G where the almost complex structure is parallel. So then this implies the Nienhaus tensor vanishes. So this is a complex manifold. And also the Kähler form is closed. So it's jointly two things in this case. So it's a genuine complex manifold, but then it's also the Kähler form is closed, so it's a symplectic manifold where these two are compatible in this because the well, I guess in general, like the skew symmetric 2 form is compatible with J also as such. So it's a type 1-1 form. So conversely, assume like you have a almost complex, almost Hermitian structure that the omega, the skew symmetric 2 form is closed, and the Nienhaus tensor vanishes, then so it's a differential geometry exercise involving the Nienhaus tensor and the formulas giving the exterior derivative that you can prove that it's equivalent. These two conditions are equivalent to the almost complex structure being parallel. So with it, we're not going to be dealing with in this talk with general almost Hermitian structures, but we will deal with one weaker case, and because we'll later in the talk, maybe the next day, I'll consider the symplectic point of view, and that involves structures that are not necessarily Kähler, but are something called almost Kähler. And so almost Hermitian structure is almost Kähler if the skew symmetric two form, the Kähler form, is closed. So it's a symplectic structure with a compatible almost complex structure. And so if it's not, so then when you have this case, then from this result, we clearly have that it's Kähler if and only if the knee and house tensor is 0. So yeah, just in case maybe some of you aren't familiar with complex manifolds. So the knee and house tensor of an almost complex structure is so the integrability so it's a torsion tensor where the general result is that by Newlander, Nuremberg, that that an almost complex manifold is complex is a genuine complex manifold if and only if the knee and house tensor vanishes. And so this is actually a local analytical result. So you have to construct local coordinates that are compatible with the almost complex structure. And then once you do that, then it's elementary. It's elementary to show that the transition mappings are holomorphic. But so with the general almost Hermitian structure, it's not a if it's not a Kähler structure, then it's not a complex manifold, and it lacks like all the like good techniques that you can employ from analytic geometry. So but what I'll talk about later will apply somewhat to this weaker condition. And it's actually, I guess, to get an idea of how weak almost Hermitian is, or I'm sorry, almost, to get an idea of how weak almost Kähler is. That if you have any symplectic manifold, has a compatible almost complex structure J. So meaning that this will be an important concept later. So it means two things. So it's compatible with J in this sense, and given this, then this is a symmetric two-form, but it's compatible if further this take it to define that this is also a positive definite. So then you have a, so for any symplectic manifold, there's compatible almost Kähler structures. So in other words, it's an almost Kähler structure. So of course, when you do this construction, it's like it's almost never, it's not going to be an integrable J. And this is so this can be done basically like a linear algebra, but it's also I guess the less technical way of seeing why it's true is so if you let this be the principal bundle of principal bundle of symplectic frames. So its fiber is not the compact symplectic group, but the real symplectic group of symplectic transformations of R2N. So. With the, I guess, standard symplectic, linear symplectic form. But if you take, then if you observe that if you quotient this by the action of the unitary group, so that the unitary subgroup of the symplectic group is the maximal compact subgroup. So that's unique up to conjugation in there. So then this associated bundle, this bundle has fibers which, when you quotient a Lie group, connected Lie group by its maximal compact subgroup, that's diffeomorphic to Euclidean space. Can't calculate the dimension off the top of my head. So this has fibers which are Euclidean. So it has a section by just like topological arguments. So this is in Kobayashi Namitsu, like the first chapter or something, Foundations of Differential Geometry. So then this, as I guess you can see the details in that book. Then this section will give a reduction of the structure group to a principal bundle of unitary frames. And so then this this then gives you the a reduction, almost complex structure that's compatible with omega. So then this gives and because omega is closed, then this is almost Kähler. So almost Kähler structure is like, so if you're doing symplectic geometry, you can always get one. I guess it's that weak. So I guess for today, I'll mostly talk about Kähler metrics. So so suppose you have a Kähler structure, then and so I guess for all cases in this talk, M will be compact. So it's the Kähler form is closed, so it's a represents a second cohomology class. And so so most of the work with Kähler manifolds consists of considering all of the Kähler metrics which are in a fixed Kähler class. So it'll have to be any cohomology class, which is also in so it'll have to be in the type 1-1 if you consider the decomposition of the cohomology with respect to the complex structure. So I'll call that by script M, and so like what I'm describing right now already is something that doesn't work in the almost Kähler case. But you typically consider on a Kähler manifold the Kähler metrics. So you're starting, so I'm starting with a fixed one, omega here. Where phi is a smooth potential function, and the new 1-1 form that you get here is well, we need this to be positive definite, which in the compact case, it's enough to say that it's non-degenerate. So its highest wedge is a volume form. I guess the reason for that is if you consider the minimum, if this is true, then you look at the minimum of phi, and then this is automatically positive definite because this is term is non-negative. And so then if it's positive definite and non-degenerate, then it's positive definite everywhere. So typically we work in with a Kähler manifold, you fix a Kähler class. So it may usually you're fixing a Kähler metric here, omega, and then you consider all the metrics that are in the same Kähler class. And so then there'll be a finite dimensional space of Kähler classes also. And this is because if you have another 1-1 form, So it's a closed form of type 1-1. So for our case, we consider it to be a Kähler, another Kähler metric in the same Kähler class. Then the DD bar lemma from the consequence of Hodge decomposition theorem is that so if you have an exact 1-1 form, then it's d I dd bar of a function, smooth function. So so the space of metrics in a fixed Kähler class are parametrized by smooth functions. And so much of the research is, most of the research on Kähler geometry is in like finding special metrics that we'll discuss, but also on the geometry of this space, which we'll consider like a different space of metrics later. So the problem, or at least the main problem in Kähler geometry is or one of them is to find a canonical Kähler metric. Say on a given Kähler manifold. So there's like many examples. So one is you can look for Kähler-Einstein metrics. So the Kähler manifold, you can basically interchange the form omega with the Riemannian metric. So so I guess there's a mild difference that if you consider this as the Ricci form, then it's a 2 form. If it's the Ricci tensor, it's a symmetric 2 form. So I'll write the symmetric version. This is just analogous to the Riemannian equation. So it doesn't involve anything about particular. So the equation is just the same equation as in Riemannian geometry, but it's a much different problem and has been solved by in many cases. So if the constant is negative or 0. So in the negative case, it was solved by Albin and Yao, and in the or I'm sorry, like in the negative case, it was solved by Alban, and in the 0 case, it was solved by Yao. Maybe he also did the negative. Okay. Around like maybe sometime shortly before 1978. And the positive case is a difficult problem, and this is so it's proved that it's equivalent to so if it's a positive Einstein constant, then it's been known for quite a while that there are obstructions to the existence. Yeah, I guess going back to like the 80s or something. But just like about 10 years ago, it was proved that the existence is equivalent to the K polystability of the manifold, and so it's polarized by the anti-canonical bundle. So in this equation implies that you need omega, the Kähler class is fixed as 2 pi times the first term class of the complex manifold. So in this particular case, like if it's negative, it's a general type manifold. So it's a solved case. If the Einstein constant is positive, then this says that that the Kähler class is positive, and so it's proportional to the anti-canonical line bundle, and so it's a Fano manifold. And so it exists sometimes and sometimes not, and it was proved by this result is Chen Donaldson and Song Sun, and I think it was in like 2012. So I guess it's a matter of philosophy whether you want to say that this solved this problem, because it's equivalent to another problem that's not easier unless the manifold has a lot of automorphism groups, then has a big automorphism group, then you can prove this stability in many cases. So I guess there's some interesting work. Ongoing. But this requires, like this particular case requires that the first term class either be, so with lambda equals 0, you need C1 0. So if it's like maybe simply connected or some, whatever that's called a Calabi-Yau manifold. And for for the negative case, you need the first term class, who's from this equation, to be negative, and then in the positive Einstein constant, you need the first term class to be positive. So represented by a Kähler form, this represented by the negative of the Kähler form, or a multiple, negative multiple. So most manifolds aren't even going to, complex manifolds aren't even going to satisfy these conditions. So, so this is maybe like the best, one of the best choices of a canonical metric that you could come up with, or a strong one, but it's not going to apply to most manifolds. So, so then you can consider just constant scalar curvature. And so that's so I'll use the in coordinates is so I added the 2 because the metric will in coordinates will have the type holomorphic, anti-holomorphic, and then also the other way in general. So if you just sum this, it's just half of the Riemannian scalar curvature. So I added 2. If you don't add a 2, you just get half of the Riemannian scalar curvature, which maybe some people do. And so then this will be equal to a constant, which will be this constant given by which is fixed by the Kähler class. So constant only depends on the Kähler class. And so then this has this existence of a constant scalar curvature Kähler metric has obstructions. So it's more general, but there's still cases where it doesn't exist. So let's see. So there's 2 obstructions. The one involves the holomorphic automorphism group. Well, there's actually more elaborate ones, like I mentioned, K polystability, but I guess that's ahead of us right now. Sorry, I think. That's kind of a lousy camera. So considering the all right. Say if it has a non-trivial holomorphic automorphisms, then say it has Lie algebra, then and so we'll consider the also yeah, I guess I don't like that notation. But we'll also consider the subgroup of so this says HAM for Hamiltonian. And so these are the subgroup generated by the vector fields, which have complex potential functions. And so but Lie algebra is this. And then so as the result, Lichnerovics that so analyzing some equations on like the holomorphic potentials that you get here, and also some Bachner formulas, you get that the Lie algebra, so the holomorphic vector fields correspond, the Lie algebra corresponding to the holomorphic automorphism group decomposes as so I'm considering real vector fields, which correspond to the type 1,0 holomorphic vector fields. That's why I have the J. Where A are parallel vector fields with respect to Levi-Civita connection, and then K here are Hamiltonian killing. So they preserve, these vector fields preserve J and the metric. And so then this tells us that this is a reductive group, or to, I guess, to be strict, like this part here, like, generates a complex torus. And so the part generated by the Hamiltonian vector fields gives you a linear algebraic group, which is a reductive linear algebraic group. And so this gives an obstruction to the existence of constant scalar curvature Kähler metric, because you can find examples complex manifolds which their automorphism group isn't of this form. So then in no Kähler class will there be a constant scalar curvature metric. So this has so, like, if you can get easy examples by, say, taking blow-ups of projective space. So maybe I'll just take the complex two-dimensional. So if you blow up, oh, sorry. Yeah, I think it's true also with the higher dimensions, but I'd have to double check. But so this is blow up at 1 point and the blow up at 2 points. Have non-reductive holomorphic automorphism groups. So these two do not admit constant scalar curvature metrics, constant scalar curvature Kähler metrics. So if you blow up at 3 points, then it admits a Kähler-Einstein metric. And you could check then that the automorphism group is like a torus and then some finite part. So it is reductive. So I guess we get to the title of the talk. I've already wasted a lot. Extremal Kähler metric. Well, sorry. So I mentioned this has obstructions. So the first is the holomorphic automorphism group, and the second is something called the Futaki invariant. And so that's a character on so it only depends on the Kähler class. So it doesn't depend on the particular metric, only on the Kähler class. And so it's a character So that means it vanishes on brackets, vector fields, and if there's a constant scalar curvature metric in the Kähler class, then the Futaki invariant is 0. So you can obstruct many more manifolds from having constant scalar curvature metrics with this obstruction also. And in around sometime in the mid-90s, though, it was found that so there was a conjecture that if a Kähler manifold had no holomorphic vector fields, then it would admit a constant scalar curvature metric, or in the Fano case, a Kähler-Einstein metric. So I guess you could prove that if I guess it's an exercise. I won't prove that if the Kähler class is proportional to the first Turing class. So if it's Fano, the C1 is negative, or C1 is yeah, I guess, sorry, just those two cases. If the Kähler class is a positive or negative constant times the first Turing class, then constant scalar curvature implies Kähler-Einstein. So that follows from the that is an exercise that you can. One way to prove it is I don't remember exactly. So using this equation, so if it's constant scalar curvature, then so here if you consider the Ricci form, then the Ricci form, which is a closed two form, is co-closed. So then it's harmonic. So I use this notation for so for Kähler manifolds, the Ricci tensor is J invariant, so it's type 1,1, and so you can go between the Ricci form and the Ricci tensor. So I write G here for the Ricci tensor. just by putting J in it. So this is a closed two form. So so the scalar curvature is constant, then it's this the Ricci form is co-closed. So that says that thus this is harmonic. So harmonic representatives are unique. So it's harmonic representing some constant times the Kähler class. And so it's harmonic representatives of a cohomology class are unique. So then you must have, this is a harmonic form representing the cohomology class. So I guess the Kähler-Einstein case is basically like the considering the case where the Kähler class is proportional to the first order class by this this remark. And so I guess to finish what I started here is around the mid-90s. Examples of Kähler manifolds with no polymorphic vector fields. And no constant scalar curvature Kähler metric were found by the work of Gang Tian. And this involves the K stability that I mentioned. So we mentioned the these obstructions. So the holomorphic automorphism group must be reductive, and then the Futaki invariant, those both involve holomorphic vector fields. So Eugene Calabi introduced the notion of extremal Kähler metric because it appeared that constant scalar curvature wasn't general enough. And so these will turn out to also not necessarily exist. So recall that so this I guess the quickest definition is that the so they're not necessarily constant scalar curvature. But if you take the Hamiltonian vector field of the scalar curvature function, so recall that the Hamiltonian vector field from the symplectic form is given, and a function. And recall that that the Hamiltonian vector field preserves the symplectic form, so the Lie derivative is 0 automatically, but we say that a Kähler structure is extremal if the vector field is real holomorphic. So that means that preserves the complex structure, almost complex structure. So in particular, it preserves automatic. So we saw it preserves automatically the symplectic form. So so it's killing. So it preserves the metric also. Yeah, the curvature. Okay, so maybe I'll say some things about the Futaki invariant. I'll suppose it is compact. And if you have a holomorphic vector field, so I'm considering real holomorphic. You could use the complex notation, but and so then this H here means harmonic. So you take the gradient and it has this decomposition, and this is because the if you take a real holomorphic vector field, and so you use the flat notation. So then this is a one form. And then you can check that the holomorphic condition means that there's a DC, this is equal to I d bar. And so that any one form which is d bar closed splits into a harmonic yeah, let's see. So any one form which satisfies this on a Kähler manifold can be written as a harmonic part, and then the exterior derivative of the smooth function, and DC of a smooth function. So DC is so any real holomorphic function decomposes like this, and so we also can write the complex potential as these two potential functions, x and so then this is the complex potential. If you take d bar of f, I guess I should have put superscript. And so this is a 0, 1 form. And then if you raise using the metric, this is then a section of the 1, 0 tangent bundle, because the metric switches types when you raise and lower. Then this is the complex gradient . So it depends on the metric. And then this, just, I'm explaining like there's a different complex picture to the real picture. So it's just basically a matter of taste. Then this will be, well, I guess you won't get this piece here. This will be, but the type 1,0 part of it. So this is, I guess, yeah, you can't get the the harmonic part with the potential functions. And so if you use the complex potential, then you get the 1,0 type. So if you want to consider like complex vector fields rather than the real vector fields. And okay, so the Futaki invariant is so it turns out that it only depends on the Kähler class and the complex structure. But that's something to prove, and I guess you can find it in the, because originally due to Futaki-san. So I'll use the complex. So this defines the Lie algebra character. The holomorphic vector fields to the complex numbers. And so you can see from the definition that that if it's a constant scalar curvature, then this is 0 here. So then this character is 0. And yeah, it's like, unfortunately, I'm already out of time today. But related to extremal Kähler metrics is that I guess basically basically like when you generalize to extremal, the Futaki invariant is no longer an obstruction. So suppose hey, this will be the last. Is extremal Kähler, then it's constant scalar curvature if and only if the Futaki invariant is 0. yeah, so it's actually like easy to prove, but it's yeah, past 12:30. So are there any questions?
Any question? Could you give us some references for the basic stuff so that
Okay.
I can post it? Of course, there are tons of references that I know, but maybe the most recent one, or
if you're new to the subject, then like if you're just differential geometer who hasn't worked with this at all, then there's like on the internet, there's Paul Kaudishan, Calabi's Extremal Kähler metrics. So it's basically like a book on Kähler geometry, to be more precise, because he explains like lots of detail, a lot of things, including different types of Kähler metrics like Bachner metrics, and so you can also find in like a chapter, I guess like one of the first chapters in Bessa, but this is going to be very out of date with the results because it's pretty old. Yeah, I guess also like there's a yeah, I forgot how to spell it, like Sekohidi.
that's a new one.
That's like a newer book on yeah, I forgot the title. It's like extremal metrics that these are if you don't want to look at the original articles. Like say if you're not new to the subject. So this one is the new, well, I guess the first and the third are both new, but this one maybe might have some more on like the stability. I mentioned like K stability. This last one would mention that. But if you're looking at the original articles, the subject goes back to like Calabi. So these were introduced by Calabi in like 1982 and 1985. So so like yeah, they're good sources still to start, even though because he introduces the subject, and there's a like a fundamental result that I quoted for constant scalar curvature case today is that the automorphism group is reductive. So there's 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 a similar result for extremal Kähler metrics, where the holomorphic automorphism group isn't reductive, but the vector field, so I said the Hamiltonian vector field of the scalar curvature is holomorphic. And so you consider that holomorphic vector field acting on the group, acting on the automorphism group, and it splits into weights. And so then you can see what the reductive part and the nilpotent part are in terms of those weights. So then you can also, that also gives you an obstruction, because you can find examples of Kähler manifolds where the automorphism group doesn't have that form, and so then it wouldn't have the extremal metric. So the original, that's contained in the 2 papers of Calabi by are both in proceedings, seminar in differential geometry, edited by Yao, Annals, 102, Princeton University Press. And then there's a second paper by in a different proceedings. Let's see. Differential geometry and complex analysis. Edited by Chabal, Farkas. A lot of the beginning, so this is like the very beginning work in the 80s. Then there's, so I mentioned like, the space of there's been like a lot of work like on this space. So the problems that I mentioned so far are just finding special metrics in the Kähler class. So this space. And so I'm going to talk about a different space of structures, like a Donaldson space that you're parametrized by the differing almost complex structures. But here you fix the complex structures and then you vary the form. So it's kind of a dual picture. And so there's like an old but interesting paper of Mabuchi, which I think started a lot of research, where this space is formally a symmetric space. And so you can define the notion of geodesic. So it has a Riemannian metric. So this infinite dimensional space has a Riemannian metric, the Mabuchi metric. And it also, you can define the notions of geodesics. And so a lot of the modern research, like in the last 20 years, has been in like the geometry of this space. So kind of like all these papers by Shushan Chen and Sakalhidi. But so if you're not familiar with the subject, it's good to probably go to the beginning, like so if you're just learning it, like Mabuchi, so that remark is if I could just find them, right? So the title is some symplectic geometry on a compact Kähler manifold. So it's Osaka. Journal. 1987. So this isn't actually though what I'm going to talk about. So next week I'll continue to get to more advanced, where you can find a lot of like what I'm going to talk about next time in Paul Gaudichan. But I'm going to talk about something which is in Donaldson, he wrote in the proceedings. Marks on gauge theory. Complex geometry. And four-manifold topology. So it's in a proceedings, Fields Medalist lectures. Uh, 1987. So in this, he talks about, so next time I'll like the original stuff that I was going to talk about, or at least much newer, is that you, the symplectic point of view is that you fix the symplectic form. So today on the space in the Kähler class, you fix the complex structure and then you consider all the metrics in the Kähler class. They all differ by a potential, so that makes it very fruitful approach to say finding special metrics. But with the symplectic point of view, you fix the symplectic form, and then I'll consider this space that's all almost complex structures. Compatible with omega. And so then, so it'll contain like, I'll use an I here to denote integrable. J, which are compatible with omega. So that means that the Nienhaus tensor is 0. So these are all almost, so this is parametric, considering the space of all almost Kähler structures with this symplectic form. And this is all Kähler structures. And so we'll see next time that like this is a infinite dimensional Kähler manifold. And this symplectic group so this is the group of symplectomorphisms of M with the symplectic form omega. So we'll see this has a Kähler metric on it, and this acts as holomorphic isometries on this infinite dimensional Kähler manifold. And then, so I guess in the Donaldson reference, he considers that space and then proves that he proves that if you look at the Hamiltonian group, so all the Hamiltonian symplectomorphisms. So in general, it'll be a smaller group. Then this acts Hamiltonian, has a Hamiltonian action on here and has moment map the scalar curvature. I guess to be exact, you have to take a particular scalar curvature when this is not integrable. I guess when it's integrable, this is the usual Riemannian scalar curvature, but if it's not integrable, so the Nienhaus tensor is not zero, then this is some like a Hermitian scalar curvature of a Chern connection. So you can consider this perspective. And this is in, maybe in the references, you can, this is in chapter 9 of Paul Gaudichan's book. So this is probably easier to read than Donaldson's paper because it gives much more details. Okay, so any more questions?
All right, thank you very much for the references. So if there is no question, we can finish here. Thank you very much. We're looking forward for the next talk.